My name is Saeed Iqbal. I'm with the Dell HPC group in Austin, Texas. Uh, I'm part of a group that develops high-performance computing solutions based on. Yes. Oh, sorry. Is it fine now? It's better. Okay. So we develop integrated solutions for high-performance computing from Dell hardware and other third-party partners. So what I'll talk today about is some introduction to the main trends we see and also some facts going towards an introduction to a new node we have developed for specifically GPU computing. That will be the focus of my talk. Then I'll give some results on the new K80 GPU and also some summary on what the applications are looking for, and also talk about the effect the switch has on the GPU to GPU communication. So starting with the big picture, as many of us heard yesterday, if you look at the latest top 500 list of the latest supercomputers in the world, about 15% of the systems are using accelerators. And this trend, as several people and several researchers have told us yesterday, that it is going to increase. It's only increasing. So the penetration of accelerators and GPUs are really here to stay. On top of that, if you look at the performance delivered from the GPUs only, so you look at the total system performance of all the top 500, and a significant amount of that is because of the GPUs or accelerators. So given these two solid facts, we can say that there is a clear goal or a clear trend towards heterogeneous solutions. So heterogeneous system architectures are due. And we're looking for the next quantum leap in performance. So as we all know, the goal is to do hexaflops / hexascale, and to reach there, it is very hard to be there with a homogeneous system, whatever that is, unless something fundamentally changes in the compute node. But that's unlikely at this time. So the only option is to go towards more heterogeneous architectures. Now, once we have that trend coming in, what are the main options out there? One thing you can do is to look at the so you can do accelerators in several places. You can do application accelerators. You can do co-processors. There are different mindsets or different points of view of doing the same thing. Or you can do application-specific hardware. So three main options out there. The current significant trend is to do graphics processing, and that is so. All this is not free. What happens is that you have to be aware of the increased power, because these are power-hungry devices. They take a lot of power, and if you put a lot of them in a GPU, in a compute node, you have to take care of their power supplies. Power has to be all the way from the power supplies, the board, and the racks. And there is a significant amount of effort that's needed to either change your code to these machines, or you want to do even to do a co-processor option. There is still significant amount of work needed to optimize and get the maximum performance out of it. So it's not that simple. In some cases, some applications have applications and licensing implications. So if you go multi-node or multi-core, then you're paying a lot. So these three things have to be taken into account when you're deciding on what kind of heterogeneity is good. So yes, we're going to be heterogeneous in long term, but which path is most likely? If you look at the if you look at the situation from a compute node design point of view, there are two categories of issues. The first is the capability issue. You have to understand that the underlying algorithm is capable of being parallelized. That's a fundamental requirement. I mean, it's very simple, but it's usually missed by a lot of people, that how much parallelism is in the application. If you have it, then you might be able to use it. If the underlying algorithm is limited, then it comes about the granularity issues come in, and how compute intensive the application is. That's important. Then you have to look at the state of the art of how much power can be provided. Yes, all these GPUs are very powerful, and they can have a high flop rate, but look at the node level and the rack level, and all the way to the data center. Is my data center capable of getting the extra power you need for the GPU or accelerated computing? So as we saw in several examples yesterday, many people had to get extra power for their data centers. Also, there is a capacity issue of how many accelerators are good for a given application class for a particular, on a single CPU. That's a hard question to answer, because it depends on your algorithm and your approach. And your implementation also, because of bad implementation, even a good algorithm will fail. Further, are you looking at GPU to GPU communication? If your algorithm is such that it's independent and the GPUs don't need to talk to each other a lot, like Monte Carlo situation or anything similar, then you can go that route. And the other route is that no, our GPUs need to communicate intensively, and now that's a different requirement. So I'm trying to show the different key issues which are out there. When you look at the practical limits of, just focus on the commodity servers, there's vast majority of the applications out there have this. So there are usually 2 CPUs per node, and due to space and power limitations, with the current state of the art and the size of the GPUs, it's very hard to fit more than 4 in a OneU server. So the maximum limit is kind of 4 per U. These are practical limits out there today. Might change tomorrow, but at this time, we're looking at 2 CPUs and up to 4 GPUs in one server. Now, given this, if you look at all the options you can design a server, so you can come out up to 7 different options. You can connect one single CPU to a GPU. You can do 2 GPUs or 3, 4, and then second CPU here. So these are the different practical configurations out there which you can make today, given 2 CPUs and up to 4 GPUs. Now, if we take the 7 ratios and the 7 options, and we select 5 of them because the other are either very imbalanced or covered by some other case, the main thing which I want to say is this, that these 5 different options out there will have different CPU to GPU ratios. So you can see the range is from 1:2 to 1:4, all the way to 2:4, and 1:4. Depending on how many GPUs are there, and depending on how many CPUs are there, and how they are connected, you get a different ratio of GPU to CPU ratio. And that's a key parameter for application performance. Applications can be sensitive to how much and how this is done. What's the ratio out there? Okay, so if we filter out only 5 configurations feasible, and so then there's a very high chance that a given application class will fall into one of these 5 different categories. For a given application class, the best or the near optimal design for the current state of the art will be from one of these 5 options. Now, so just hold that thought in your mind for a while, and we'll come back to it after the hardware introduction. Now, the goal of the study, which I'll show you some results on, is to, given these 5 options, these 5 configurations, how can I understand the performance and the power, the trade-off between more performance and more power consumption, or less power and less power consumption. Also, if I want to maximize the performance per watt metric on a given system, then what are my options out there? So I'll try to introduce the hardware used. First thing is the K80 GPU. This is a slide that shows at what rate the GPU has evolved from its previous generation. So if just one generation ago, that's the K40, you see that, okay, first of all, the K80 today is about 3 to 6 times more powerful than the most powerful CPU out there. And that's a big motivation for changing the whole, that's driving the whole, trend towards GPU computing. That's a big motivation, and a lot of people can, based on this, invest effort as well as resources to get this done. Anyway, the increase from just one generation ago is substantial increase in the cores to 73%. Memory has doubled, the bandwidth is increased, and the power, and even this is most important, is the double precision teraflop rate. That is 30 to 60% better from the previous generation. So with this huge increase from K40 to K80, and the trend is likely to continue, I mean, it further solidifies the idea that you really need GPUs in the servers. We have a server that is a OneU server, and it is specifically designed for high-density GPU computing from the start. So it's not something we retrofitted and from other markets for HPC. This is a special box for HPC. Now, the 4130 this is a picture showing the server. It has an array of GPUs. So this is the front side of the server. So air flows here in this direction, and you will see the fans. Then there's a module switch. I'll come back to that. And the CPU here, plus InfiniBand and power supplies in the backside. Okay, so this server, the C4130, offers the 5 configurations out there. So now here, if you look at the 4 GPU configurations, we call them A, B, and C. With A and B, you have an additional PCI 96 lane switch in between. So the 4 GPUs are connected to a single CPU. In the B configuration, we have 2 CPUs, and they connect through the same switch. The C configuration has 2 CPUs and 4 GPUs. And here it's connected in a balanced fashion. So there are 2 GPUs per CPU. So just the A configuration is very economical because it has just a single CPU and 4 GPUs. You save the cost of extra CPU if that's okay in some applications. Then there is the C is most balanced, as I mentioned, but it has no switch in it, so there's no need for an extra switch. So these are the 4 configurations that have 4 accelerators. Now with 2 accelerators, we have D and E. D is a single GPU to a single CPU connection, and with E you have 2 GPUs connected to a single CPU. So this is more of an entry-level starts when you're starting. It's very simple configuration. This is more balanced with 2 GPUs. So these are exactly the 5 different configurations we talked about previously. This is how the server looks like. Here you'll see 5 different system configurations offered in OneU, 4 GPUs in OneU. That's kind of rare in industry. But you see the single CPU here with the fans. The GPUs are here in the front, and the rest of the power supplies are needed back here. Same. This is a C configuration with 2 CPUs and 4 GPUs. Right? Just I wanted you to have a visual picture of how the thing looks like. The unique features are to maximize acceleration. The main feature is that the GPUs are in front of the server, which is unique because airflow goes from the front to the back, and the cold air comes in, and it's the GPUs that get the cold air first. So, so the fans are here, and by the time it reaches the CPUs, it's warm, but that's okay. Because in conventional servers, what happens is it's flipped around. The GPUs are in the back, and by the time air reaches GPUs, it's already warm. And as you know, GPUs are sensitive to temperature. They will throttle, and then the performance will go down just because there is less, the temperature is not right. So here, I must say that the GPUs are treated as first-class citizens. They are given priority. The second thing is that in case there is a shortage of power, then power is not throttled from GPUs, it's actually throttled from CPUs, which is also a unique feature because mostly the CPUs are always given full power, but GPUs are throttled. So with these two features, you can expect that GPUs will have full power, and they will have the best available temperature or the best available air coming in, and these 2 points will slightly enhance the GPU performance, because bulk of the work is done on GPUs. So it's good that we can give them the first class. What I want you to take from this introduction is that the main feature of this box is flexibility. Okay, flexibility to get the different configurations, as well as number of GPUs to CPUs ratios. We support most main accelerators and coprocessors. So if you give an application class, whatever your optimal configuration is, we will either have it exactly or something very close to it. Okay, so now I'll talk about some performance results. So we took this server with 5 different configurations here, A, B, C through E, and then this is CPU only number. This side is performance, and this side is power. And this is for HPL. The peak is in this box here, and the acceleration is shown here, as well as efficiency is shown here. So there's a lot of information out there. But this is a key slide because if you look at HPL, it's very compute intensive. And it's commonly used as a benchmark. We saw that for 4 GPU configurations, A, B, and C, B and C are pretty close, but actually C is the best. C is showing 9.08x acceleration over reference of a CPU only. The B configuration is very close to that, but it is slightly less in this case. In some applications, it's switched. Here we have the A configuration. So this delta is because of 1 less CPU. Remember that this had 1 CPU and 4 accelerators, and this thing has 2 CPUs and 4 accelerators. So this delta is because of the CPU that's missing. It's almost this size. So this is the picture here. Now on the 2 GPU side, we have the balanced configuration D is doing better. It's giving an acceleration of 4.7, and the entry level is not that far away. So on the power side, you can see that this is a CPU power consumption. Performance per watt is around 4 gigaflops per watt when you look at the 4 GPUs, and 3.5 when you look at 2 GPUs. The power ratio or power consumption is 3 times. So you're getting 9x acceleration in your application or SPL for an extra power of 3x. So it's still a good deal from look at it from the power performance angle, because you're getting 9x performance for 3 times more power. It's a very good deal. Anyway, so what I've done is we have tested applications and this. So now I'll say a few words about molecular dynamics. So this is one of the very commonly used molecular dynamics application. Here, NAMD. So in this case, lower is better, because this is days per nanosecond, and most of you already were. So with one of the benchmarks, you can see that the acceleration is again, the competition is between B and C in this case. But C configuration, that's the most balanced, is still suitable for NAMD and the K80. With B nearby, same picture on the power side, you are getting 2x power power draw, and for about 7x performance. So remember that last time we had 9x because that's the benchmark, and this is a full-blown application. So now we have 7. So again, the ratio is 7 to 2, showing the original thought that why we should be using GPUs. It's confirming those results. Again, that B is very close to the C. So it might be the case that in some future optimization, you can see B doing better or as close as C. But at this instant, with the latest versions out there, this is the picture. We ran the same data, on K80 lamps. This is another molecular dynamics application, mostly used in government labs. And so here we saw a very good performance, about 16x improvement from a single CPU compared to a single CPU for C configuration. And the power is 2x. We did similar, so it seems like this application is again favoring on the side of balanced configurations. Because most of the softwares have been designed, most applications are designed with the balanced view in the mind, so it's possible that most applications will favor. But in Gromacs, which is another molecular dynamics application, we see that the B configuration is showing much better results than the C configuration. And this is because of the way the Gromacs processes are launched, because it looks for different resources and launches processes on the second processor and uses the current processor to run GPUs. So this is a different application showing that B configuration is winning in this scenario. On the 2 GPU side, we have the balanced again winning here. So it seems like this is very sensitive to the ratio of GPUs to CPUs, and 1:4 ratio of GPU to CPU is winning in this case. So we did a home D run. Here we have again C doing much better than A and B. One thing is that for 2 GPUs case, D and E are similar. So it seems that it's not very sensitive to the number of CPUs. It only cares about the number of GPUs here. Okay, so ensis is a very common CAE, CFD kind application out there. We have the, okay, in this again, lower is better. So now we have two different benchmarks. Let's talk about the larger one, that's 9.6 million fluid pipes. Here we have, again, tight competition between B and C, but C is winning and B is very close. What we should note that this result is for a 2-core run. It's not for an entire full CPU. It's very important that I mention this because the licensing model of ensis is such that it's different for a 2-core and when you run all the cores on the CPU. I believe it's very expensive to have a full license that will take all the cores in a CPU. So most users are confined to just two cores, and then compared to that, you can get a much better performance improvement. Instead of buying more licenses, which can be very expensive, you can go and get hardware acceleration, which might be less expensive. So here I have a summary of all the runs. What I did here was the performance and the power and performance per watt. We separated the, say, HPL and apps so that we can get a sense of what's going on at an average level. So overall, we see that for C configuration, for compute-intensive HPL-like benchmarks, C is better, and even for applications, the performance is, I mean, if you're looking for absolute performance, it seems that C is the best bet here. If you're looking for, so the power consumption between B and C is similar because the resources are similar. So both have 4 GPUs and 2 CPUs. So total power consumption will be similar. Interesting thing here with the power performance per watt, because the performance is different here. So performance per watt between C, which is the 4 GPUs, and D is very close. In fact, D is better. So when you look at the performance per watt point of view, and if you want to maximize your performance per watt, then even you can consider a balanced 2 GPU option out there. So the same, the usual absolute performance and performance per watt choice is available. You can go with absolute performance, or you can do maximization or optimization on the performance per watt analysis here. So on average, you're looking at about 9x performance, and power increase is 3 and 6. This is for the 4 GPU set, A, B, and C, and this is for the 2 GPU. So basically, at the final analysis is that with K80s and using this new server, you can get about 9x performance on HPL at the cost of 3x more power. And even the performance per watt is increased to 3.6x. Okay, so now I'll talk about another feature. What we have here, as I told you previously, is a switch, the 96-lane switch that connects a single CPU to 4 GPUs. Okay, it's a non-blocking switch, and we studied what is the advantage of that switch. So we compare configuration B with C. So B has the switch. It has 4 GPUs connected to a single CPU, and this configuration is more balanced. does not have the switch. Now, if you look at the switched configuration, which is B, the bandwidths, GPU to GPU, so each K80 has 2 GPUs internal. So you're looking at 8 GPUs in a system, and you can see GPU to GPU bandwidth. So I took out the data for internal because it will be very high and it won't show. So this is local communication, GPU to GPU 1 to 1, and then between, 1 to 2 and 3, 4. So you see that the bandwidth between all available GPUs is pretty much the same in the switched configuration. So that can be an advantage for applications that are bandwidth sensitive. All GPUs have practically the same bandwidth. It's a very small difference here. On the other side, if your application is not sensitive to bandwidth, then what you have is a tiered approach. So if your GPU is within the same card, like the same 1 to 2, same K80 card, then you can expect higher bandwidth. If you are on the same side of the, if you have the same CPU, same root complex, then you have this. And if you have to go across to the CPUs and talk to the GPU on the other side, then there is a slightly less. So you have a 3-tiered bandwidth. Now it depends on the application. If it is sensitive to this kind of GPUs, the bandwidth differences, some cases it may or may not. But the thing is that the option is out there, and it depends. It's up to the user to select the best, or test and then select which configuration is best. Okay, so we did measure the bandwidth, the host to device and device to host bandwidths for the different combinations. So for example, here the C configuration has 2 CPUs and 4 GPUs. So you have 8 different pairs of host to device. And we measured all of them. The bars that are missing are because they don't exist in that configuration. So for example, A configuration has only a single CPU. You cannot have the second set because there's no point. So the point of this slide is that the theoretical maximum is here, which is around 15, and what we are getting is about 12, which is kind of the maximum you can expect practically from these connections. So another thing is that it's balanced across all. There is no degradation of bandwidth because of the weird combinations or the different settings. Same story with the device to host bandwidth. So how are we doing on time? 10 minutes? Okay, so what I'll do, I'll skip over the K40 results and take you directly to the summary. Yeah. So we have similar summary for what we have for K80. Similar result for K40 was done. And in this scenario, again, we see that there is a big difference between the HPL, the compute intensive, and the applications. The main architectural difference between K40, as you all know, and K80 is that K40 is a single internal GPU, with K80 has 2 internal GPUs connected with the PCI. So if you have 4 K80s, then there's an additional layer of switching that needs to be, that is built in before. So the 4 GPUs are connected in pairs, and the pairs are connected through the switch. You can expect around 5x performance with K40s with about double the power, so and about 2.5x in your performance per watt for 4 GPU systems. Yeah, we can skip this, and yep, I want to leave some time for questions if you have any. Yes. Well, see, the cost is, I cannot talk about the cost at this time, but I'm an engineer. I don't worry about the cost aspect. But sure, if you can give me your contacts, I can put you in contact with the marketing guys, and they can tell you all the details. But it will be competitive, and it will be good. Don't worry about that. Well, are you interested in K40 results or? Yeah, I can show you one of them, like HPL. On HPL, you have the same picture. You're looking at C configuration, giving you a 6.4 times the acceleration. Now, here we see that the B is doing a little worse than what it did for K80. On the GPU, on the 2 GPU side, it's pretty much the same picture. D is better than E, and the balance configurations are winning. So for compute intensive loads like HPL, I mean, we can expect that the balance configurations will win, and that's what we saw. On the on NAMD, again, they're very similar for between B and C. So it needs to be kind of optimized. I think the code is optimized for C because of the previous designs, but now with the newer technology, it might come in that you can see B doing better. Lamps is again the same. Oh yeah, this was more of again here because the it's very sensitive to the number of GPUs. It doesn't really care about CPUs. So when you have four GPUs, your performance is practically the same for 2 GPUs as well as for 4 GPUs. The power is different, so it's interesting that the power will be slightly higher for B compared to the same performance. So maybe the C configuration is better or A is better depending on where you're coming from. Gromacs, we saw that we saw that B is better here than C. That's because of the nature, how it's run, and the internal processes, the way they are launched, and the way the load is divided among the GPUs and CPUs internally has this phenomena. Okay, ensis is pretty much the same picture. This also the same. We already talked about this. So here we have 3 tiers because we have only 4. Sorry. Oh, sorry. You mean this? These two? These two? Yeah, so here the power consumption is the average power consumption for HPL. Yeah, SW is the switch. So it has the switch module in it. The B configuration needs a switch to connect the 4 GPUs to it. Yes, it has 4 accelerators. So in C configuration, you have 2 GPUs connected to 4 GPUs, two per CPU, without the switch. Yes, it will affect the. True, that's a good point. Yeah. We have not studied the I/O part. I can show you the. Let me go back to the configurations. And I can show you that. So this is B. Okay, 4 GPUs connected through a switch to a single CPU. And these are two different CPUs, 4 GPUs connected to it. So that was the difference. When I say SW, it means that this configuration has a switch in it. And it has a small power draw too. That's why it has to be mentioned. But it's not like a CPU or a GPU. So I hope that's clear. Go back. Yeah. Okay, I guess that's all I have.